All right, this time we're going to complete the warm-up. Pause the video. Here are the answers to the warm-up. Step 1, put it in your calculator. Find an easy zero. Synthetically divide. What you're left with goes from x cubed to x squared. You can then use the quadratic formula or factor. Final answers. All right, so our steps in a linear, very straightforward to-do list. Try to factor. You're going to see grouping reappear. Okay, so if you are still cloudy on grouping, please come and see me. Cloudy on grouping, come and see me. Maybe I'll try to make a video just on grouping. Might be a good idea. Look for easy zeros from the calculator, which are the steps that we took in the last example. Use synthetic division. Make sure you have all of your placeholders. If it starts with x to the 5th, x to the 4th, 3rd, 2nd, first power, constant. If not, use your zero place filler. Solve the remaining polynomial. The goal here is to always take these big polynomials and break them down to at least quadratics. We can work algebraically with quadratics pretty easily. We have the strategies to work with those. That is the only time you can revert to the quadratic formula, when you're dealing with an exponent of 2 at the maximum. What's different in this unit is now that we have introduced imaginary numbers, we can find all zeros. So in the previous unit, we talked about finding the real zeros, which means the square roots were always positive. Now we could use a quadratic formula and have it result in a negative underneath the root, and we don't stop. We keep going and include complex numbers in our answer. Okay? So this is going to include imaginary solutions. All right, let's take a look. Specifically now, we're going to focus on finding zeros through factoring. 2 examples here. Example 1. How would I do this by hand with no calculator? What's the first type of factoring I should employ? Greatest common factor. So go ahead and factor out an x. That should leave you with a basic quadratic, which then also factors, or does it? It does not factor. So what do we need to do? Quadratic formula. Okay. So to save time, here's your quadratic formula. Okay. You put everything in, it results in a negative 7 underneath the root. That negative 7 becomes I root 7. So the new part of this is basically taking this, which becomes a negative 7, and converting it into I root 7. Does anyone have a question about the I root 7? Yes, ma'am. I'm confused. What do you mean, am I using? Am I using it on this, you're saying? I can't use it on this because this is x cubed. I can only use quadratic formula on a quadratic expression. Okay? All right, so working our way down, we do all this work. However, if I go back to my original problem, how many zeros does the exponent indicate I should have? 3. So this counts as 2. The other one is a 0. It's generated from setting x equal to 0. Questions? Gary, do you know these are in your notes in the packet? Okay, just check. All right, now, example 2. Please put a star by this. We're going to start to see more examples like this one. We did go over this in the prerequisite unit. Again, the factoring is back. This is not a quadratic. X to the 4th is a quartic equation. However, if you look at the form of it, x to the 4th, x squared, and a number, we can model off of quadratic factoring, or what we call binomial factoring. That's when we do the parentheses, the baby parentheses. So we start out with this by saying, okay, I'm going to do it up above actually. What times what gives me x to the fourth? X squared. Okay. Now, as soon as you start to write this, you need to have a little bit of a forward thought and say, all right, I'm factoring now, but I may need to factor again because I could come up with a difference of squares, like an x squared minus 9. So keep that on the back burner as we start to do this. What two numbers multiply to give me negative 12, but add or subtract to give me negative 1, negative 4, and a plus 3. Right now, when we have these parentheses, yes, you could further factor. You could take x squared minus 4 and turn it into x plus 2, x minus 2, which would give you 2 zeros. But if we just take the first quantity, set it equal to 0, and the second quantity and set it equal to 0, it's going to look like that for the first, that for the second, and then we just solve those using the square root method. Notice here, plus or minus the square root of negative 3. We used to say that didn't exist. It was unreal. We're allowed to get non-real solutions, provided we write them in the complex form. So the two solutions I'm looking for are plus or minus 2 and plus or minus I root 3. Any questions on that? All right, I'd like you to try these few by hand, and we're going to go over them. In the first example, it's very similar to example 1, I believe it is. But example 4, this one is not like the one that we've already done. This is going to be done via grouping. So let's see who knows how to group. Like assistance with the grouping, let me know. Give me a couple laps here. And that could be in a section of the test. You will find there's a time when grouping in calculus will save your life. It will save you so much time and energy that you'll be so thankful that you have it. And you'll start to use it more and more. Yeah, just take the second quantity here, set it equal to 0, and solve the square using square root method. We're starting to talk, so that means we're getting it done. Here are my two answers. Would anyone like to see any part of either? Yes, ma'am. Okay, so I did switch something up on you. It's not under the root. But here's the reason why. Do you remember when I introduced complex numbers, I said they're in the format of a plus bi? Yes? When you do quadratic formula, you get something like 1 plus or minus the square root of negative 7. I'm just making this up off the top of my head over 2, for example, right? And then you go and you put the I out front. You keep the 7 in here. And you make this plus or minus, and you bring the I out, correct? Well, root 7 is actually a coefficient of the I. So what you're seeing here is now we're transforming this into 1/2 plus or minus root 7i over 2 so that it matches this form. When you do the square root method, like here, right, you would get the square root of negative 15, bring the I out front, but the root 15 is actually the b value, which is the coefficient of I. Okay, so the I is not underneath the root. Okay, so I transitioned into that with this slide, yes? You can. I'm not going to take points off, but when you look at the answers, just recognize that they do mean the same thing. This is the more formal solution in complex number form. I will tell you at the moment we are looking at process, the process of finding zeros, not the product or the answer, the form of it at the moment. Okay? All right, so if you need them, there's the work. Yes?
On the grouping, how come the x minus 3 is like square root? This is true.
Because think about like when I have a, b minus cb, don't I take the b out front? It's only 1. It just so happens that instead of a single variable, I'm taking a quantity out front.
Oh.
And I just happen to reverse the order and write it second because they're interchangeable quantities when you write the order. All right, now let's talk about the solutions. We're right now all the way up on the top diving board platform. It's not a diving board, it's a platform. We're about to jump off. So what we've done now is we've connected what we did before to what we're doing now with imaginary numbers. And we want to take a look at the two solutions that we have. If you take a look, notice that any time we go to imaginaries, there's always 2 of them, right? There's always 2 of them. So we have a general rule we can extrapolate from that. And it says if a polynomial has one complex zero, a plus bi, you should always assume, because it does, have a second zero that is a minus bi, which is the conjugate. So in other words, imaginaries always come in pairs. Always. For zeros. All right, so let's play a game. Let's see if we can translate this to something that actually applies here. If I tell you 6 minus 3i is a 0, what's the other 0? 6 plus 3i is a second 0 that I don't have to tell you because you need to know it will always exist. So if we have a list, if I had to say, oh, a function has 8 zeros, if I give you this one, this would be a second one. You know that automatically. There's no thinking about it. There should be no mystery about that. And I don't have to give you both. I only need to give you one to indicate that there's the second one automatically. Okay, that's what this statement is translating to for you. Sound good? All right, moving on. Find all the zeros of this. Take a look. Okay, remember I said right up there on that high platform. Here we are. Notice we ramped it up. We went to a 5th degree polynomial. We don't do these by hand. Factoring is not going to help us. So what do? We go to the graph. All right, I'll go to the graph. Then what do? Go to the table. You got it. There you go. What does the table tell us? Look at the picture, look at the table. Look at the picture, look at the table. I have it up here. So if you're not putting it in your calculator, really connect the ideas, not the nuts and bolts of putting it in the calculator. What do? Find what? Find the easy zeros. Okay, what are they? I'll highlight them. 1 and -2. So here's -2, and here's 1. What can you tell me about 1? It touches, so what do we know about 1? Has a multiplicity of at least 2. So if I think about this, find all the zeros, my first thought should be 1, 2, 3, 4, 5, correct? My second thought, after looking at the picture and the table, is how many zeros do I know right now? Great. What are they? -2, 1, and 1, right? Okay, now let's take a time out. Does anyone have a question about how I knew that just from the information that's on the board? I can repeat it again if you missed it. Yes. How did I know there was 2 1s? Because this comes down and turns back up. This is a touch. Indicates a multiplicity of 2 or 4 or otherwise. Okay. Anybody else? All right, so all of that, this problem, you putting in your calculator, you coming up with this, that's all background information from the previous unit. Now, how do we take x to the 5th and break it down into a quadratic that we can work with? How do we take that information and mathematically move forward? Synthetically divide. So I actually am going to need a couple synthetic divisions, right? I'm going to need to divide by that, take my answer and divide by that, take my answer and divide by that. So every time I want to take x to the 5th and continue to break it down. Do I have all of the descending powers? What am I missing? I have 5, this is a 1, 4, 3, 2, 1, and 8. Correct? So don't forget your 0. Start here. I want you to work all the way down. Yes, sir. Nope, it would not matter, but you do have to have the 0 placeholder. When you get to the bottom, when you get to your final answer here, it should all come out to the same. Also, as a refresher, when you're doing your synthetic division, which I'd like you to do now, your remainders must come out to 0 or you're making a mistake. See the powers? The 5. There's no x to the 4th. So it would be 0x to the 4th technically. Have all of them represented. Break it down, have fun. Alright, so what am I left with? What does that 104 mean? We went from x to the 5th to x to the 4th, x to the 3rd. This is now x squared plus 4, so it looks like this. Set that equal to 0. Square root method, x squared equals negative 4. What is x equal to plus or minus I, what? 2i? Plus or minus 2i. So there's my 2i and my negative 2i. Yes, you can write them as plus or minus, just illustrating the concept that there are 5 total. All right, any questions? Anything in purple? Questions on? All right, I believe example 6 is a you try 100%. Go ahead and do that, and I will also tell you that the answer is this. So let's see if you can generate that. You work it out. Again, double check your placeholders. Use your calculator. Don't forget good friend grouping. This is one of those that shortcut exists. Bothers you when it doesn't line up with the floor. It's gotta be straight. Are we feeling pretty good? Like everybody had a 2-3 with this to get here? Yes? Breaking it down? No? Okay, I'll take one more lap. You can ask questions. If you're not getting that. Stay in the middle because I can never walk through there. Alright, so we're good now. We're feeling good? Yeah? Like we get it? Alright. Here we go. Read the problem. Example 7. Alright. Now, this is a very typical type of test question because it's going to involve about 3,900 steps. That's not why I would give it to you. It's actually because I want to just prepare you for the tediousness of calculus and making sure that you don't make sign mistakes because the problems you have to do there are very, very long. So that's why I like this as an indicator of, your ability to kind of see things from beginning to the end, follow through, watch your signs, take your time, etc. Based on what we said before, we know that there should be 4 zeros, correct? In general? 1, 2, 3, 4. So as you read through the problems, start to kind of put down on paper some of the basic facts that you already know. One of the facts we know is that 1 plus 3i is a 0. That indicates what else is also a 0 automatically. 1 minus 3i. Okay, now, this is one on the test I always get in a debate with someone about. Well, shouldn't I get half credit? I got half the answers. Well, let's see how much work it takes to get the other 2 answers, and then we'll really look at how we assign kind of points based on the things that we do. What did we do on the previous example once we indicated what the zeros were? Once we had a 0, what operation did we use? Synthetic division. Same thing. So I'm going to use my synthetic division. I have all my powers represented. So I have a 1. Please space this out. I have a -2. I have a 14. I have a -8. And I have a 40. My first synthetic division is going to be by the given 0 that they gave me, 1 plus 3i. Now, what do we know the remainder should come out to? So when I do this, what should I get in this box?
0.
A 0. That is a given. That needs to happen. And you want to do all of the work to make sure that you get a -40 right here. All right, follow suit. I bring down the 1. Now what? Multiply 1 times 1 plus 3i. That's easy. What do I get? 1 plus 3i. All right, so I'm going to write 1 plus 3i. Now, if you think back to our lesson 1, this is, I can add these together if I add the real parts. It just so happens this blue number doesn't have an imaginary part. So when I add the blue to the red, what do I get? -1 plus 3i. This is where the panic starts to ensue. I can feel it coming, the anxiety. Just take a breath. What's our procedure say? Take the number in the bottom and multiply it by what's up top here, correct? So I'm going to do that work on the side over here. 1 plus 3i times -1 plus 3i. I know it's not the same, but do you see this as difference of squares? Can you see that? If I reorder these a little bit on the insides, it's difference of squares. But if you don't, we would just FOIL, correct? We would get -1 plus 3i minus 3i plus 9i squared. The middles cancel. And what is positive 9 times I squared? What's I squared? Negative 1, so this becomes negative 9, negative 1. Doesn't that give me negative 10? That's not bad. This times this is negative 10. That looks good. That was a lot of work, miss. That was a lot of work. Now what? Add, bring down the 4. Don't worry, the reward is coming, and it's not just feeling good that you got the problem right. What do I do with the 4? Procedurally multiply by this, so we're going to distribute. We get what? 4 plus 12i. Combine like terms, there's no imaginary part in the blue number. So I get what? Negative 4 plus 12i. All right, now don't cheat here. Don't cheat. Don't just write minus 40. Make sure this works out, or all the rest of this isn't going to work out down below. So if I do a quick multiplication here, 1 plus 3i times negative 4 plus 12i, I get negative 4 plus 12i minus 12i plus 36i squared, which happens to give me negative 40. And my marker's done. Okay, so luckily this gives me negative 40, which does give me 0. Now remember when I said it's coming. Silver lining is about to show up. Here it is. Because I had all this work here, the next time I synthetically divide, it is not all that work. It will look like it in the setup because I want to synthetically divide by what now? 1 minus 3i. But you're going to see, because I've reduced all these numbers and provided myself with some complex numbers in the problem, it isn't as much work as what we've already done. So if I come in here now, I bring down the 1, multiply 1 minus 3i. What do you see starting to happen? Everything, this is going to cancel to 0. Keep going. This is a 0. Bring down the 4. Multiply here, I get what? 4 minus 12i. Do you see how easy that second part is? Comes out to 0 here. What does this last line of numbers mean? I went from x to the 4th to x to the 3rd to x squared. So this is 1x squared plus 4. X squared plus 4 equal to 0. X is equal to plus or minus 2i again. And there are your 2 other answers. 2i and negative 2i. This is where that whole argument of, look, miss, I got 2 answers. I should get half credit. No, you got to do all this to get most of your points. Now, I would say you could get 1 point for remembering the conjugate, but the rest of it, no. Yes, sir. Your brain caught up? Okay. Are we good?